All right, hello everyone. So today we are going to be looking at the next form of operations when dealing with radicals. So at this point, we've looked at multiplication of radicals and division of radicals. And so now we're going to expand our understanding and look at addition and subtraction. So the first thing we have here is actually a warm-up that we're going to do to kind of help us get better prepared for the lesson at hand. And we're actually going to change these first couple of examples. So if you already did these ones, I apologize. We're going to go ahead and scribble these out. Actually, just the first two. So we're going to take both of these out here, and we're going to replace them with slightly different problems. And when you see these problems, you're probably going to think, wow, these weren't too bad or anything along that lines. We're going to work to kind of simplify these understandings and work with them a little bit. So the first problem I'm going to give you guys is going to be a 2 parenthesis. Let's go with a 4x plus 9y minus x. Okay, and then the second problem I want you guys to consider, let's go with, we're going to go with a 2a plus 4 times a y minus, sorry, let's change that to a b. I forgot we were doing a and b. B minus a plus c. And on the very end, just to kind of change things up, we're going to add a plus 3c. Okay, so these are the two problems that I want us to take a look at. And they do serve a specific purpose again in today's lesson. So looking at the first example, you might notice a couple of things. In the parentheses, we actually have a 4x and a minus x. So that's something we could simplify into a 3x plus 9y. And again, keep in mind, we're not dealing with exponents here. This is just a 4x minus x. We have 4 x's and we're subtracting 1 x, leaving us with 3 x's. If it was multiplication, this would be a different story. It would become a 4x squared because x times x becomes x squared. But this is just subtraction, so we combine like terms, the 4x and the minus x. Then at this point, you would go through the process of distributing, giving us a 6x plus 18y, and the 6x and the y cannot be combined, so that would be our final answer. And again, I'm stressing some points to help us later, but the x and the y are different, and therefore I cannot do the 6 plus the 18. Let's take a look at the second problem I wrote for you guys. This one's a little bit longer, but it's pretty much the same math. We're dealing with a lot of A, B's, and C's. Looking at the parentheses, there's not much I can kind of do. Please remember PEMDAS. PEMDAS. So we should do parentheses first, which there's not much we can do. Exponents, which there are none. Multiplication and division. So we do actually have some multiplication happening here. So we can do this and make it a 4b minus 4a plus 4c. And then on the end, we still have that plus 3c, and out front, we have that 2a. In which case, now we're at the point of combining like terms. We have a 2a minus 4a that can get combined. So that actually will become a negative 2a. As far as the b's go, we only had one b, so we have the 4b. And then as far as the c's go, we have a positive 4c and a positive 3c, giving us a positive 7c. And again, each of those cannot be combined because one's an A, one's a B, and one's a C. Next thing we're going to look at here, and again, this is keeping with the ideas of variables happening, is a reminder of FOIL. Take a moment and ask yourself, do you know what FOIL stands for? What does the F stand for? The O, the I, and the L. This should stand for first, outside, whoops, outside, inside, and last. Which means we're going to take the first number over here and multiply it by the first number over here, giving us an x squared. And then we're going to take the outside number over here and multiply by the outside number over here. That's a negative 4x. Inside, we take the two inside pieces right next to each other to give us a positive 4x. And then the last one's 4 times negative 4 gives us negative 16. in which case we're at the moment where we can combine like terms. So these actually cancel out because that's a negative 4x and a positive 4x, giving us our final answer of x squared minus 16. Now the second example, I'm not going to do all the way through at this moment, but I do want to point out that anytime you see that squared, a lot of times people are like, oh, I distribute. That's a big no-no, okay? What you actually have is a 2x minus 9 written twice. Squared means that you have two of the exact same thing. So you write it twice, and then you'd have to go through the process we just did of first, outside, inside, last, okay? So the point I wanted to make there is the idea of squared. So now that we have some background knowledge, which again seems slightly irrelevant at this current moment as far as radicals go, but let's go down and take a look of adding and subtracting radicals. And actually one of the crazy things with adding and subtracting radicals, whether it involves a variable, like the first example, or whether it involves a number, doesn't actually change how the problem is solved, okay? So keep in mind what we did up here in the warm-up, this idea of combining like terms. So I really want you to focus on the idea of how do we do 2a and the minus 4a. We did the 2, we did the minus 4, that gave us 2. But notice that our a did not change. Same thing with the c. 4 plus 3 gave me 7, but the c did not change. So a lot of times the variable does not change, but the numbers out front do. That's the case whenever you're adding or subtracting radicals. So the first thing you'll probably notice up top here is the idea that you must have the same index, that's the little number out in front, and you must have the same radicand, which is the number underneath. Again, both vocab words we saw on the first day. Okay, so when we look at the first example, again, it has the same index, 3 and 3. It has the same radicand, x and x. So if we were multiplying, this would be different. You'd multiply the radicals and stuff like that. But with addition and subtraction, think of this almost like having a 5a minus a 3a. If I had a 5a minus 3a, you would say 2a. And the same is true with this radical. Because these two pieces are the same, it's almost like having an a and an a. They're exactly the same. So in your answer, they will not change with addition and subtraction. Again, multiplication and division are different, but with addition and subtraction, they will not change. So 5 minus 3 would actually give us 2, just like over here. And then rather than just having a nice simple a, like we did over here, we actually have a cube root of x, and that's our final answer. So in summary, sorry, that was supposed to erase. There we go. In summary, these pieces here, the radicals, need to be exactly the same. And that's what it's kind of saying up here. Not only does it need the same index, but it needs the same radicand, or number underneath. And when these radicals are exactly the same, when we're adding or subtracting, all we have to do is look at the first couple of numbers. Okay, so let's look at another example here. In the second one, these are both square roots, and they are both the square root of 7. So because they match, we can add and subtract, in which case we're going to do 2 and the plus 3 giving us 5. And then again, the radical does not change, and that's going to stay the square root of 7. And that's your answer. The only time the radical underneath changes is when you do multiplication. Okay, and I bring you back to the idea of what if these were variables? If I had a 2x plus 3x, you would say 5x. So the x does not change. If I had 2x times 3x, not only would I get 6, 2 times 3, but I would get an x squared because it's multiplication. So whenever we're multiplying, yes, the radicals will change, just like variables change with multiplication. But with addition, the variables stay the same, and same is true with the radicals. Okay, so again, with radicals, adding or subtracting, they need to stay the same. Now looking at the next example, there should be a red flag. These two radicals are not the same, okay? They are both square roots, but they're not both, square root of 7 or square root of whatever. They're different. And you're like, okay, great, I can't do them then. Okay, you can't. Right now, you cannot do anything with them. But what if we simplify? So let's look at the 18 and simplify it for a second. We can break that down into a 9 and a 2. 9 times 2 is still 18. Square root of 9 is going to give me 3, and then the square root of 2 will stay square root of 2. Then let's say that I look at the 32, and I say, can I simplify 32 at all? And let's think for a second. Let's try 16 and 2. That would give me 12, carry the 1. There you go, 32. In which case, square root of 16 gives me 4, and the square root of 2 will stay square root of 2. And look at that. Upon reducing those fractions, we actually end up with a problem that both have a square root of 2, which means we can now use our rule of 3 minus 4 gives me a negative 1, square root of 2. And a reminder that square root of 2 does basically just tag along all throughout the problem. It's just like the one we looked over here. 2x plus 3x gives you 5x. Or if I had a 6x minus 2x, you would get 4x. So the x kind of just keeps tagging along throughout the entire problem, and it does not change when you find that common radical. So then both having the square root of 2, your answer will also have a square root of 2. Now let's take a look at the next one. This one has 3 pieces to it, and there's an added factor here, okay? So let's just do one at a time. Let's say that we look at this first one here. Something you should notice is that the 6, there's a 6 out front, right? But for now, that's actually not going to affect us. Let's just focus on the 18, priorities. So with the 18, I can break that down into a 9 and a 2. Square root of 9 is going to become 3 square root of 2. So again, the 18 will become a 3 square root of 2. But what about the 6? Please do not forget about the 6. He actually gets tacked on to the front, keeping in mind that everything here is multiplication. So the 6 square root of 18, they're technically being multiplied to each other. The 4 square root of 8, technically that's multiplication. 3 square root of 72, technically that's multiplication between the two. So when I change the 18 to a 3 square root of 2, I then bring down the 6 and make it multiplication, giving me a final reduced version of 18 square root of 2 for the first piece. Now I can take a look at the 8 and again do the same math. So this is going to break down into a 4 and a 2. Again, that gives me 2 square root of 2, but do not forget about the 4. Carry him down, and now I have 4 times 2, giving me 8 square root of 2. And then for the last one, dealing with a slightly bigger number here, 72. For this one, we can break this down into, let's try a 9 and an 8. Actually, I think we can go bigger than that, right? Let's go, I think 36. Looks bigger. 36 and 2 gives us 72. That's beautiful. So that's going to give us a 6 square root of 2. But again, and this one's actually negative, so don't forget the negative out there with it too. We're going to bring that negative 3 down here. Do a little multiplying. So negative 3 times 6 is a negative 18 square root of 2. And then sure enough, square root of 2, square root of 2, square root of 2. So they are all square roots of 2. So now I just need to do 18 plus 8 minus 18 gives me an 8. And then don't forget that square root of 2. Just tacking along the whole time. With addition and subtraction, that is what we focus on. Now the next one's an interesting one. If you stare at it, it does the same thing. It has a 4 out front and a 3 out front. But there is something more important we should notice. Stare at that for a second. Is there anything else you notice about this problem? Well, check this out. This is a square root of 15. This is a cube root of 15. They are actually different. So 1 is a square root and 1 is a cube root. And when we see that, that means that we cannot actually add these. So even though they both have a 15 inside, 15 and 15, one is a square root, one is a cube root. That means their indexes are not the same, and therefore I cannot simplify this. So you can write, no answer. Sometimes I see people write out the exact same problem to acknowledge the fact that, it's still an equation, or I guess it's still a problem, but it's not one that can be simplified. So the fully simplified version is exactly how it's given to you. And the last one, again, these are just some noteworthy characteristics you'll see in different problems. This last one, when you take a look at it, again, double check. They are both square roots, perfect. And they are both 2's, perfect. So in theory, we can add these, no problem. But this is one that it's very tempting for people to say square root of 4, and they simplify it down to 2. Do not do that. Got to be super annoying here. You cannot do that. If I was multiplying these, then yes, 2 times 2 would give you 4. But in this case, I'm adding them. So we need to add the numbers that are out in front. In which case, we have a 1 square root of 2, okay, because that's the number that's out in front, even though we don't see it, plus another 1 square root of 2. So when I add these, rather than getting a square root of 4, we're going to get a 2 square root of 2. That will be our final answer. Okay, because it's, again, what we're really doing is adding those numbers out in front, but the square root of 2 travels with us all of the way. So in general, those are the things that you're going to see when it comes to radicals. I should say more specifically adding radicals. And now we're going to move on to the next page. And this is where it's going to step up a little bit more. Okay, so in the first part here, we have foiling of radicals. And you'll notice this actually comes back to the idea of multiplication that we did a little bit. We did a little foiling in the warm-up. So if you need to go back to that and recall what FOIL stands for. Foiling radicals is no different than foiling anything else. Again, it's just like having an X in there and trying to FOIL it with an X involved, okay? So if I FOIL this first problem that we see here, and it says, do you know how to FOIL radicals? We're gonna see. You're gonna take your first ones, just like before, nothing fancy going on there. So 3 times 2 gives us 6. So that's first. Outside means take your last one times your first one times your last one. This one's interesting because you have a 3 times this 4 square root of 5, in which case the 3 and the 4 are both outside radicals. They're not really even associated with radicals, so we can multiply them to get 12. And the square root of 5, unfortunately, he's just going to tack along there. Inside, we're going to see a similar math happening here. The 2 square root of 5 times 2 will give us 4 square root of 5. And then last but not least, we have the 2 root 5 times the 4 root 5. Watch what happens with this one. This one's kind of cool. 2 times 4 gives us 8. And actually under multiplication, remember, multiplication, the radicals will change. Square root of 5 times the square root of 5 will actually give us the square root of 25. In which case, this is fully FOILed now, and we can start to combine quote unquote like terms. So the 12 square root of 5 can be combined with the 4 square root of 5. So let's go ahead and get 16 square root of 5. I'm going to leave the 6 chilling out front here. And then this last piece here, this 8 square root of 25, we actually know what the square root of 25 is, in which case that will just become a 5. And now I have 8 times 5 giving me positive 40. And that's kind of that. Now there's actually one other thing we can do after doing this 8 square root of 25 and getting 40. We have a 6 and a 40. Those are both whole numbers. We can add those to get 46. Add the 16 square root of 5, and you have your answer. Okay. Now we're not going to work all the way through this next problem, but I do just want to remind you from what I mentioned in the warm-up. This is squared, so we're actually going to have 2 of these. Okay, so rather than trying to distribute that square, you actually need to write it twice, and then you will begin your FOIL process. Boom, 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 boom. If you're looking to find the answer to that one because you want to try it, I see now I did not post the answer key yet. Let me pull that up real quick. Sorry about that. I'll have to find the answer key. Sorry, I thought I posted that. I'll get that posted here in a moment. But check under the answer key. It should be posted under Content Library Week 31. Again, I'll have that up momentarily. I just realized now I don't have that posted. That's okay. Okay, so if you're looking for the answer of that, I'll get that out to you guys. And the last thing we need to talk about today is conjugates. Okay, so a conjugate is basically exactly what you saw happening up here, but check out some of these examples. These two things are conjugates of each other. These two things are conjugates of each other. What do you notice about these? What do you think a conjugate means? Well, looking at these two things, they're actually exactly the same. 2 square root of 3, 2 square root of 3, but one is addition and one is subtraction. One is addition, one is subtraction. So a conjugate means that we're taking the exact same numbers and doing one addition and one subtraction. And when you do a conjugate, it's going to look exactly like we did with the foiling. So I give you an example of a conjugate here. 2 plus square root of 3, 2 minus square root of 3. And actually, I think just for the purpose of saving us some time, we're going to look at the second one instead. Okay, it's still conjugate. This is a positive, this is plus, this is minus. But since we didn't do the foiling up here with 2 radicals, let's do the foiling down here with 2 radicals. Okay, so this one's a little bit different because rather than having a 2 plus square root of 2 or something like that, these are both radicals. So when I start multiplying this first, that's going to give us the square root of 25. Outside, that's minus square root of 10. Inside, plus square root of 10. And then last, that's going to give us a minus square root of 4. If I start combining some like terms, so we do have the negative square root of 10 and a plus square root of 10. Those actually kind of cancel out, right? So plus square root of 10 minus square root of 10. The square root of 25, I'm going to go ahead and simplify that down to a 5. And then over here we have a minus square root of 4, so that's actually minus 2, giving us a positive number of 3. So check this out. When you do a conjugate, this is a big one, when you do a conjugate, you will always get a whole number as your answer. Versus a non-conjugate, so looking at the problem up here, this is a non-conjugate because these are not exactly the same and one being positive, one being negative. You do not get a whole answer. You actually get a square root involved there. If we did this problem, it will also give you a radical in your answer because this is a minus and so is this. So a conjugate meaning you have a plus version and a minus version of the exact same thing. This is the exact same thing. Square root of 2, square root of 3, square root of 2, square root of 3, but this is a minus and so is this, meaning it's not a conjugate. Okay. The only time your answer works out to be a beautiful, simple whole number is when you're dealing with a conjugate. And as our last topic of today, I come back to this idea of rationalizing the denominator. So it actually says here, think back to when we rationalized the denominator. If I look at the second example, and again for time, I'm just going to go right into that second example. When you're looking at that second example, as we mentioned when we looked at rationalizing denominators yesterday, you are not allowed to have a square root or cube root or any radical in the denominator ever. So right now, this square root of 2 is a problem. In the first example, it would not be hard for us to get rid of that by simply multiplying it by a square root of 3. That would give us the square root of 9. Square root of 9 simplifies down to a nice whole number. Okay, that's what we looked at the other day. But with this second example, it doesn't work out as nicely. Do not write this down. This is just for argumentative purposes. If I multiply by this by a square root of 2, you have to keep in mind you're multiplying the whole thing by a square root of 2, which means on the bottom, I'm going to get a 3 square root of 2 minus 2. That does not help us. Our goal here is to get rid of that radical in the bottom, and by multiplying by a square root of 2, it just doesn't happen. So let's go back to what I just said a couple seconds ago. We want the denominator to be a whole number. So looking at our examples up here, was there one that always gives you a nice, beautiful, simple whole number? And your answer should be like, oh, yes, Miss Maurer, it's a conjugate. And that's perfect. So looking at this problem, again, keeping in mind the denominator is the only one that's giving us an issue, not the numerator. 2 plus square root of 2 is beautiful. That's fine. It's just that denominator because it has a square root. So if I multiply it by the conjugate, the plus version of the denominator, then I should get a beautiful, simple whole number. Now remember, whatever you do to the bottom, you do have to do to the top. Keep it fair, guys, okay? So yes, the top doesn't really want it or need it, but because I need to multiply the bottom by the conjugate, I need to multiply the top by the exact same thing. So no, do not multiply the top by a 2 minus square root of 2. Do not do the conjugate for the top. Just focus on the bottom. So do the conjugate on the bottom. Again, you might need to pause the video and work this through a little bit. I'm going to move a little quick here to wrap things up. In which case, if I FOIL this, I would do 3 times 3 gives me 9. 3 times the square root of 2 is going to give us a 3 square root of 2. Then a negative 3 square root of 2, and then a minus square root of 4. On the top, yes, you're going to have to FOIL again. It's not going to be as pretty, but we're going to do it anyways. So that's 6 plus 2 square root of 2 plus 3 square root of 2 minus the square root of 4. Doing some simplifying, the 3 square root of 2 and the negative 3 square root of 2 cancel out. This 4 is actually going to become a 2. So I have 9 minus 2 gives me 7 on the denominator, which is beautiful. That is a beautiful whole number. It's simple, everything. There's no radicals. It's perfect in every way, shape, and form. On the top, if I simplify a little bit, square root of 4, I just wrote that as a 2. I can do the 6 and the negative 2. That gives me 4. And then I can do the 2 square root of 2 and the 3 square root of 2, giving me a 5 square root of 2. And that will be your final answer. And the whole reason we did that is so that we no longer had this icky yicky square root of 2 on the bottom. So by multiplying it by its conjugate, we got rid of the square root in the denominator, got ourselves a nice, simple, plain, whole number, no radicals, which is exactly what we wanted. We really don't care much what happened to the top. It still has a radical, that's fine. It's just a matter of what happened in the bottom. Okay, so hopefully this helps you some as far as adding and subtracting radicals. Again, keeping in mind that they do have to have, they do have to have the same radical and index for us to add them, like in that last example. And then the second thing we learned about was FOILing these, which yes, is a little bit of multiplication, but it involves knowing how to add and saying that a 12 root 5 plus a 4 root 5 gives us a 16 root 5. So you can see how FOILing kind of needs both multiplication rules and addition rules. And that is all for us today.